from University Tate Münster, who will be telling us about Bachstedt periodicity and DVRs.
Right. So let's get right into it. So what do I mean by Bachstedt periodicity? So let's recall that for ring R, we have Hochschild homology, which is defined by taking you can take the derived tensor product of R with itself over Z. So I guess like if you're free over R or something, this is the usual tensor product. Otherwise, you have to derive this. And this now acts both like on R itself, because basically an action of this is just a bimodule structure. And so you can compute this finite tensor product, somehow like the homology of this augmented algebra, if you will. And the homology of the resulting chain complex or whatever, or homotopy groups of the resulting spectrum, if you want, that's what we call Hochschild homology of the ring. So as an example, if R is Fp, then what is the derived tensor product of Fp with itself over Z? So I wrote R up there. For a non-commutative ring, you have to somehow take like the opposite guy here. For a commutative ring, R op is canonically equivalent to R again. So what is this? Well, if we resolve Fp over Z, we have like this two-stage resolution. We write Fp as the cofiber of multiplication with P. So this is gonna have like homology in 2 degrees, 0 and 1. Both of them are Fp. They're just the tensor product and Tor. And this is actually as a DGA equivalent to, equivalent to an exterior algebra in a generator of degree 1. So what will Hochschild homology will be? Well, Hochschild homology is going to be computed by tensoring Fp with itself over this guy. So there's going to be a bar complex that computes this. The bar complex over Fp of an exterior algebra. And as I'm sure most of you know, if you take Tor of an exterior algebra, what you get is a divided power algebra. So let me write this like this. This is the free divided power algebra on one generator. And explicitly what this looks like, so what are the homology groups of this complex? Well, they're going to be generated by X and other elements, which are like the divided powers on this guy. Since we're p power torsion, that's since we're p torsion, we only have the p divided powers. Everything else is multiplicatively generated. And then you divide out by like the p powers. So pretty complicated algebra multiplicatively, I guess. Okay. So now this is ordinary Hochschild homology for, let's see, I guess, okay, there's a better button to do this. So what about topological Hochschild homology? So what I'm actually going to talk about here is THH. So it's a similar definition for R, a ring spectrum. And for example, you could take an ordinary ring considered as the corresponding Eilenberg-MacLane spectrum. So instead of Fp, you could consider HFP. Then THH of that ring spectrum is again defined by a similar formula. But here, you want to tensor over the sphere spectrum. So this guy, as an underlying spectrum, this guy is going to be like the smash product of R with itself. And then this has a finite algebra structure of which you compute like a bar construction again, I guess. And So as I said, ordinary rings give you perfectly interesting examples. And for ordinary rings, this is not ordinary Hochschild homology, because here you're not tensoring over Z, you're tensoring over the sphere. So, and I guess now I want to write, I want to write the Einberg-MacLane spectrum HFP just as FP, like just consider abelian groups as a full subcategory of spectra. So I'm just going to write FP, but in this context, think of it as the Einberg-MacLane spectrum. So for FP, what's this FP tensor FP over S? Previously, over Z, this was just an exterior algebra. Here, this is the homotopy of, like the homology, the FP homology of an Einberg-MacLane spectrum. So this is huge. This is the dual Steenrod algebra. And since this is already much more complicated than the exterior algebra we got while working over Z, you're pretty scared at this point that THH is just going to be all over the place. So that's not the fact. So here's a theorem due to Böckstedt, which is that the homotopy of THH-FP is, as a ring, just polynomial. So it's even simpler than the thing we got while working over Z. And I first want to explain a little bit how to think about this theorem. So of course, we're going to talk about generalizations later, but let me explain to you how to think about this. So here's a more structural way to think about the spectrum FP tensored over S with FP, instead of just via its homotopy groups. So the claim is that FP tensor over S with FP, regarded as E2 algebra over FP. So this guy is an FP algebra, say via the inclusion of the left factor. There's another FP algebra structure on it, but we just make a choice. So this guy is actually free on a generator of degree 1. So in other words, like a more canonical way to write the free E1, the free E2 algebra on a generator in degree 1 is, well, as like FP smash the suspension spectrum of loops 2s3, but with the ring structure coming from the E2 structure on loops 2s3. And the claim is that there's an equivalence of E2 algebras over FP between these two. And if you know the Mahowald description of HFP as a Thom spectrum, that's very closely related to it. This is somehow that statement on homology, but multiplicatively. And you can, in fact, deduce either one from the other. So this is not, I'm not saying this is a terribly new statement, but it's a very nice perspective for what's about to happen. And so if you want to prove this, can I somehow erase part of it? Let me just erase the upper part. So if you want to prove this, well, if you want to show that something is free, you get a map for free, right? Because maps out of free things are easy. So the proof is, well, you compute pi1. That's, well, just FP. And then this gives you a map from the free E2 guy. And you want to show that this is an equivalence. And that's, of course, a computation in the end. But it turns out that Dyer-Lashoff operations give you the full structure. So somehow you can compute both sides with Dyer-Lashoff operations, like the homotopy of both sides together with the action of like Dyer-Lashoff operations. And that actually tells you, like for the left-hand side, this is like Kudo Araki and Dyatlashov. And for the right-hand side, this is in the H infinity volume. This is work of Steinberger, I think. And it turns out that both sides are generated in the same way under Dyatlashov operations by degree 1 stuff. So it turns out that if you have a map between them that's an iso on pi1, which we have, it's an equivalence on homology. It's a computation, but one that's relatively clean. You can cite it away out of these two references. And so if you input that, that's a pretty nice description for the for this FP tensor over S with FP. So this immediately allows you to prove Böckstedt's theorem. So how do we do that? Well, we just identify the bar construction on this guy. So that's by definition THH. We identify this with the bar construction on this free guy. And then by general formulas on how the bar construction behaves well with colimits and so on, you can actually write this as, like, you can pull in the bar and get like the bar construction in spaces here. And that's just loops S3. That's the free E2 algebra. So, and the homotopy of that, you know, it's polynomial in one generator. I guess it's a general fact that if you take the bar construction on a free En algebra, you get the free En minus 1 algebra on a shifted guy. But it's kind of nice to express it in terms of loop spaces. Okay, more generally, Böckstedt holds for K a perfect FP algebra. So think of other finite fields. You still get that THH of K, pi star of that is polynomial on one generator. And you can actually deduce it from the version of Böckstedt's theorem we just saw a proof of by some base change arguments. You don't need to find like a fancier version of that proof. Follows from it. Okay, so in the line of this thinking, we want to understand THH for other ordinary rings. I mean, I guess I haven't motivated why we want to do that, and I'm not going to talk a little bit about, I'm not going to talk too much about that here, but for example, there's a close relationship between algebraic K-theory and THH that doesn't work with ordinary Hochschild homology. So somehow working over the sphere here is the right thing even for ordinary rings. I guess one way to, one hint in favor of that is already that we just saw that THH is simpler even for rings such as FP. Okay, so now what I actually want to talk about in this talk is THH of discrete valuation rings and quotients of discrete valuation rings. And so what do I mean by that? So I want to talk about, I want in the rest of the talk, A to be a complete mixed characteristic discrete valuation ring, and think of examples such as ZP with some stuff adjoint, or I guess Witt vectors of a finite field, which is I guess also of that form, stuff like that. If you don't really know what the discrete valuation ring in general is, you don't need to know for this talk. It's think of these examples: ZP with some stuff adjoint. Mixed characteristic just refers to the fact that these guys are p-torsion free. So somehow they are a little bit like characteristic zero stuff, but they also have a maximal ideal modulo which they suddenly become characteristic p fields. And the maximal ideal in these examples is generated by p or these other elements. So in this setting, in a discrete valuation ring, that's always the case, that the maximal ideal is generated by, like, it's the principal ideal, it's generated by one element, and that element is called the uniformizer, like it's unique up to units. So we're going to call that pi. Okay, so and a mod pi is always going to be a perfect field, so that we require. A mod pi perfect field. Okay, so in this setting, we want to talk a little bit about THH of A. So you can think of the p-adix, for example. So this is pretty complicated. We're going to see later what it is, and this is computed by Lindenstrauss and Madsen. But it's kind of hard to write down a nice formula for it. What we saw in the previous section is that THH of A mod pi is like polynomial. This was like the homotopy of that was even, generated by one generator, and so on. So if you want to understand THH of A, you might try to first work relative this element pi and try to get something about that. So I guess the first people who had this idea were Jacob Lurie and Bad Morrow-Scholze. Bad Morrow-Scholze write something about it. Jacob expressed this to Thomas at some point, so I think they both independently had this idea. So what do I mean by relative? Let's make a definition here. I want to define a ring spectrum S adjoint Z, sort of the polynomial ring over the sphere, and I just want this to be the suspension spectrum of the monoid of natural numbers. So this is not a polynomial ring in any way. It's not free, since the natural numbers are not free as an E infinity ring. I guess it is free as an E1 thing, but it's actually a commutative ring spectrum. It's not free, but it looks nice. It's just a wedge of infinitely many spheres. And for some ring R, which is a S adjoint Z algebra, like a commutative ring spectrum over S adjoint Z, we're going to define the relative THH as the same kind of tensor product as before, but now we tensor over S adjoint Z. And the intuition is that this S adjoint Z somehow is like a map out of S adjoint Z somehow picks out an element in R. At least if R is an ordinary ring, a map out of S adjoint Z is exactly giving an element of R. And so we're kind of thinking of this as working relative that element. And in fact, what we suggested here works exactly, namely that if we have such a DVR with uniformizer pi as above, and we take the map of ring spectra from S adjoint Z to A. Remember, by that I mean the Eilenberg-McLean spectrum with pi 0 given by A, that sends Z to pi on pi 0. There's a unique such map by some abstraction theory. Then the THH of like this relative THH, at least after P completing, is really polynomial again. So this is kind of a version of Böckstedt periodicity of this theorem we saw earlier for FP for this mixed characteristic kind of guy. But we have to work relative. And the proof is basically by reduction mod pi. So there's a couple of base change formulas. This kind of relative THH, if you take this mod pi, you take the cofiber of the element pi, you get in homotopy. THH is always a module or even an algebra over the ring you formed it on. Then you can also write this as some kind of base change where you base change from SZ to S. So take cofiber Z because Z acted as pi, or equivalently, well, I guess not, no, yeah. So this, if you base change this, the thing you're working relative with, you can actually work out that this is the same as doing ordinary THH. So THH relative S. The notation is a little clumsy, but like this means relative. Ordinary THH of the base change guy, of A mod pi. And by Böckstedt's result, we understand that. Like by Böckstedt's result, this guy has homotopy groups polynomial over A mod pi. So in other words, let me erase the top part. In other words, the claim we made, we've at least just checked mod pi, right? We made the claim that the homotopy groups are all even and all given by A in each even degree, and we've just checked this after reducing mod pi. And now, since THH of A, well, THH of A relative S adjoint Z is an A module, and in A, the ideal P is a power of the ideal pi. That's a general fact about these discrete valuation rings, somehow that the pi, at least on the level of ideals, always looks like some kind of root of P. This tells you that the P completion is also pi complete. So somehow, I'm sketching this a little bit here, but somehow like the equivalent, like the identification we wanted to show is an identification between things that are complete with respect to pi, and we know this to work after reducing mod pi. So that's how you show this. I guess you have to produce a map, but that works because the polynomial ring is free on one generator. Okay. So this is nice. So even in these things that look more like characteristic zero, we do get something like Böckstedt's result. And you could similarly hope that if we now consider stuff such as this guy modulo a power of the uniformizer, for example, if you take A to be the p-adix, you get rings like Z mod P to the K. So you could hope that for those guys, it still somehow makes things simpler to work relative this element pi, even though taking cofibers with respect to it is not going to be nice anymore, right? Because this is now not pi torsion free. And in fact, it works out. So what we can show is that for such a guy, the relative S adjoint Z is actually pretty simple again. It's again concentrated in even degrees, and now it has one polynomial generator of degree 2 and one divided power generator. And you can show that by writing A prime as this kind of tensor product. You have like this ring S adjoint Z. You can consider cofiber Z to the K on that guy. And if you base change that to A, you get the cofiber of pi to the K on A, so A prime. And this gives some kind of similar decomposition on THH, on this relative THH, because here you've tensored over the base you're working relative with. So then THH actually decomposes in this kind of way. So here you're going to get THH of S adjoint Z mod Z to the K, and then this thing relative S adjoint Z. I don't like this notation either, but for some reason semicolon was already, or like comma was already taken for something else. Okay, and then you should think of this guy as contributing the polynomial generator. And this guy has to do with like the Hochschild homology of truncated polynomial algebras relative to the polynomial algebra. It's not the same, but somehow like we're base changing to a Z algebra here. So this is somehow related to this, and that guy is just a polynomial guy. So you can, from some kind of Kunev formula, get our claim. Okay, so that's nice. So the takeaway there is that if I'm over perfect FP algebras, Böckstedt tells us that THH is very nice, much nicer as ordinary Hochschild homology, for example. But if you're working over something that lives not over FP, but over some discrete valuation ring, you can still get away with similar statements by working relative to the uniformizer in this way. And now, of course, the question here is, what does this actually get us? So what we actually want to talk about here is usual THH. So we want to get back. And the curious thing is that it actually, like there is a very simple formula, but it goes the other way. So you can describe this relative THH by taking the absolute THH, since R received a ring map from the ring spectrum S adjoint Z, this THHR is an algebra over THH of S adjoint Z. And there's also a map from THH of an E infinity ring to the E infinity ring itself. So in this tensor product formula of THH, think of this as just tensor, like just multiplying your factors together. And the commutativity of the ring somehow enters in this actually factoring over the tensor product. There's another nice description of this of THH in terms of this cyclic bar complex. So you can think a little, you can think of THH as something like you have configurations of points on S1 labeled by elements of your ring, at least morally. And then the space change formula is something like, in this guy, every element, like every point still has their own copy of S adjoint Z in it. But then the space change somehow forces all of them to agree. So that is more like we're working relative S adjoint Z now. Don't know if that helps anyone, but for me at least, that was like the only way I could ever remember where this formula, like how this formula works. So if R is also a Z algebra, so for example, if it's just Eilenberg-MacLane, if it's just concentrated in a single degree, as in all the examples we're studying here, we can further identify this with a tensor product where we're not just tensoring over THH of S adjoint Z, but we also sneak in another factor of Z on both the thing we're base changing over and the thing we're base changing to. So that doesn't change anything. And now these two things are both pretty nice, right? So this Z adjoint, like Z tensored over S with this guy, well, that's just Z adjoint Z. By which I mean, again, the Eilenberg-MacLane spectrum. So it's like concentrated in degree 0. And the other thing, if we base change THH of S adjoint Z along S to Z, what we get is THH of Z adjoint Z relative Z. The original THH was relative to the sphere. We've base changed from the sphere, so we have to also put that in our base somehow. And now this is just a fancy way to write Hochschild homology. This is the Hochschild homology of Z adjoint Z. So this is really, this has pi star I guess if you think about Hochschild homology in terms of chain complexes, then I should write H star, but you can form this in spectra, and then pi, like it's gonna be some HZ module whose homotopy is the homology of the chain complex. And then this is just as a graded algebra, Z adjoint Z, and then you get an exterior guy, which I'm going to call DZ, in degree 1. So this is concentrated in degree 0 and 1. In both of these degrees, it is just Z adjoint Z. Now, we somehow have a nice, simple base change formula, this one, that gets us from absolute THH to relative THH. How do we get the other way? Well, as all of you know, if you go in one way easy, the way back is some spectral sequence, right? The Adams spectral sequence gets you back from homology to homotopy. And somehow, like, if you want to go from simple stuff to hard stuff, it's always a spectral sequence. So that's the case here too. So we can construct a little spectral sequence whose input is exactly what we just input, like such a S adjoint Z algebra, which is also a Z algebra. So one way to write this is just say it's a Z adjoint Z algebra, R. But again, think of the examples we've considered. There is a multiplicative spectral sequence which takes the following form. The input is this relative THH tensored with an exterior algebra. So you just adjoin one exterior guy, and you get to THH of R. So this is kind of a cheap spectral sequence, right? It just has two lines. So you could also write this down as an exact sequence, but for the multiplicative structure, it's nicer to package it in this way, or like a long exact sequence, right? And because it's such a finite spectral sequence, like there's no convergence issues, and it's also compatible with passing to p-completed guys everywhere. So similarly for p-completed guys. That's important because we've like what we've understood relative S adjoint Z earlier was only after p-completion, at least for DVRs. For the quotients, it doesn't matter. And the construction is not very hard, right? You just want to somehow involve the space change formula from earlier. So you can write THH of R as a stupid base change, where you just have this this same guy as before, and then you just take it again, right? That's just for trivial reasons, THH of R. But now we've seen that this guy has just homotopy Z adjoint Z in degree 0 and 1. So you take the Postnikov filtration on this guy. And that's why this also plays nice with multiplicativity somehow. The like Postnikov truncation stuff behaves well with multiplicativity. So since this guy has like two homotopy groups, this gives two shift, like the associated gradient of the tower you get just has two copies of THHR base changed to Z adjoint Z. So if I write that as before, I can write it like this. And by what we saw earlier, this is exactly the relative guy. So we've produced a filtration on THHR with a filtration whose associated gradient is two copies of this relative guy. All right. So now, finally, let me tell you a little bit about what we can compute with this. So let's first reproduce what Lindenstrauss and Madsen can tell us about THH of DVRs. So let R be of this form we considered earlier, where A is like a complete mixed characteristic DVR with perfect residue field. Then the spectral sequence takes the following form. We saw that the relative THH is polynomial. And now we only adjoin this exterior guy, DZ. So we have two lines like this. Everything is determined by our D2 differential. And now it turns out you can algebraically D2 of X. You can algebraically describe D2 of X. That's because in low degrees, topological Hochschild homology and Hochschild homology are closely related. Like the first group agrees. And so the formula you get is such a DVR you can always write as a certain extension. You can always recover it from its residue field K by, well, adjoining this uniformizer pi and dividing out some minimal polynomial. So somehow this A is always some kind of algebraic extension through the uniformizer of Witt vectors of the residue field. So for example, if your residue field is just FP, you can always write your discrete valuation ring as an extension of the P at X by some polynomial monic polynomial. And then this THH1, at least the p-completed one. So let me be careful and write this as THH of a p-completed. This is just going to be generated as an A module by this element dz, and the relation you divide out is the derivative of your polynomial. It's kind of funny how that comes out. There's something to do with that Hochschild homology has some relation to Kähler differentials. But anyway, so if you believe this formula, that tells us exactly that D2 has to hit this element. So since everything is like, I guess, what do I want to say? This tells us that up to a unit, D2 of x needs to hit this guy. And I guess we haven't really narrowed down x in the previous statement, so you could as well pick your generator x, like renormalize it for this to hold on the nose. So this also determines a generator in a nice way. So what does this give us? Well, let me erase this lower part so the spectral sequence still stays. We can, by multiplicativity, infer all the differentials from this one. So more generally, since the differential is going to be a derivation, we get that this hits n times e prime times dz. And now we can just read off the thing the spectral sequence converges to. There's only one non-zero entry in each diagonal. Like this is Serre grading. Sorry, I should have said that earlier. So what we get is that THH, or at least the p-completed one. Let me again. This is A for star equals 0. It's A mod n e prime for star equals 2n minus 1. And it's 0 else. So for example, if you do this for the p-adix, you can recover that it's torsion in odd degrees. And in fact, you can reconstruct THH of the integers from that by some fracture square arguments, and actually get back this result that THH of the integers is z mod n in these odd degrees. Somehow it looks exactly like the thing here. Because I guess in the p-adix case, the polynomial e is just monic of degree 1. So in that case, this factor is just 1. But for more general, like for ramified guys, you get other factors here. So it's kind of interesting. Right. So that's one example. And let me quickly tell you about the other one. So I said we can do quotients of DVRs. So one example is z mod p to the k. And in that case, the spectral sequence is going to be more complicated, right? Because there the relative guy was already polynomial times divided power. So here you're going to get 2 generators, and then it goes on, gets more complicated. But again, we can describe all differentials. And it turns out that d2 of x is just dz, and d2 of y. And then I really have to tell you what the divided powers go to, but the differentials are compatible with divided powers in this situation, which is something we can work out. That's some extra information. You can describe this, and it turns out you can recover like there's a classical paper by Brun which computes this via some other much more complicated spectral sequence. You can completely recover his description and get additional information about multiplicativity by analyzing what happens here. The main idea is that you can form this element y prime, or let me call this y. Yeah, let me call it y prime, but it's not derivative. You can form this kind of linear combination of y and x, and that guy is now a cycle and has divided powers, because somehow the coefficient here is like divisible by p enough. And if you combine this, you can actually use this to write down a different base for this polynomial tensor divided power algebra, and show that to get some description of the form that this is a divided power algebra tensor, something you can explicitly compute. There's some like certain orders that correspond to like kernels and co-kernels of multiplication with n in degree 2n minus 1 or something like that. Okay. And the cool thing about these methods is that we get a completely general description that's just valid for all A prime quotients of DVRs like this, which is that THH of A prime is like what the spectral sequence computes. So we can write this as the homology of some DVR that looks like A prime adjoint a polynomial generator, an exterior generator, and a divided power generator relative some like module like with respect to some differential that we can explicitly describe. And it's kind of interesting to analyze how this behaves. So there's, for K large, this looks like Böckstedt's result a little bit, like there's a divided power generator that splits off. But for K small, you have a polynomial generator that splits off. And the interesting thing is that if A is sufficiently ramified, so that's not something that happens for the P adix, but if you adjoin some roots of P or something, then there is an in-between case where it seems that there's not really a closed formula for what you get. So there's an explicit DGA computing it, and it's not hard to do in examples, but it's kind of interesting that like the results you get can be pretty messy. Okay, so I think that's all I wanted to say. Thanks for your attention.
All right, I'm going to unmute everyone so we can thank him. Okay. And then I'm going to go ahead and remute people so that cuts down on the background noise. And then we'll open it up for questions. Any questions for Achim?
I have a question.
Mm-hmm.
So when you wrote down the spectral sequence, you said that a version also exists for p-complete things.
Mm-hmm.
Can you just clarify, like, is this for like ZP adjoin Z algebras R, or can you just write down the p-complete version of this thing?
So the information so let me erase this. So the input is still, so what I mean by this is that the input is still a Z adjoint Z algebra R, but then I'm saying that there is a spectral sequence that where the input is pi star of the p-completed relative guy tensor in exterior algebra, and it converges to pi star of the p-completed guy. And the way you get this is you construct the same filtration, but then before taking homotopy groups, you just p-complete everything. So this is just a little observation that because there are no like infinite towers here or something, you still have a spectral, like you still have a convergent spectral sequence if you apply p-completion to the tower before passing to the spectral sequence. This is just because for the examples we're considering, at least for the DVR case, not the quotients of DVR case, we can only really control this guy after p-completion. But the input is still the same. You can do this for any Z algebra with a choice of some element, basically.
Thank you.
Okay, other questions? Well, I have kind of a, oh, go ahead, Dominic.
Yeah, so what about, say, the equicharacteristic case? Do you guys have anything you can say in that case?
Yeah, we have worked that out, so it is in our paper. It's not too interesting though, because somehow in that case, the differential is always 0, right? Because you have a map from THH of FP to THH of A in that case. And somehow like there's a guy X in pi 2 here that hits the guy X here. So somehow the differential on the X is trivial. And there's an additional subtlety, which is that in the equicharacteristic case, p completion and pi completion is not the same anymore. So you have to be kind of careful how you phrase things. So somehow it's more interesting, and the statements are a little cleaner in the mixed characteristic case.
Okay, thanks.
Okay, it looked like maybe Jay, did you have a question also?
I was just going to ask something very naive. So do your methods shed any light on the cyclotomic structure, THH?
We're working on that. It's a little tricky. So for example, this filtration that gives us the spectral sequence is really like a square zero extension. It's as multiplicative as it can get because it's like you've applied the Postnikov tower. But the cyclotomic structure is not Z-linear anymore. So multiplicativity is becoming a little subtle and so on. But if you write this just as a fiber sequence, then we do know that it's cyclotomic, but the cyclotomic structure on the fiber is a little subtle. So we're working on it, and it looks like you can say something, but it's looking a little tricky.
Okay, thanks.
Okay, great. Any other questions? Okay, great. Well, that will wrap it up for today.